Hello, this is the third part of the chapter Periodic Properties. Now we will start crystal or metallic radii. In a metal crystal, we can think of the atom arranged as a set of touching spheres. In fact, a large number of atoms are closely packed. They are held together by means of metallic bonds. The bonding is metal is not understood compared to bonding in ionic and covalent compounds. The metallic radius may be defined as one half of the distance between the nuclei of two adjacent atoms in a metal crystal. The intermolecular distance between the nearest neighboring atoms in a metallic crystal can be determined by X-ray diffraction. Thus, we half the distance between the two nearest atoms, we get the metallic radius of the atom. So, the radius of metallic radii is equal to intermolecular distance between two adjacent atoms in a crystal divided by 2. Alkali metals from well-defined metallic crystals. The alkali metals exist as diatomic molecules in the vapor state. The interatomic distances in the metal crystals and in the metal diatomic molecules are given in the table. Let's start ionization energy. In order to promote an electron in an atom from one energy level to the next energy level, the some energy must be applied. If enough energy is available, the electron be removed and a cation with unpositive charge is formed. The amount of energy needed to remove the least tightly bound electron from a mole of gaseous atom is called ionization energy. The process can be represented as the ionization energy is measured conventionally in kilojoule per mole. It is possible to remove more than one electron from the atom. In such cases, the process can be expressed where E1, E2 and E3 are the ionization energies that are needed to pull out the electron one by one, which are known as first, second and third ionization energies respectively. Ionization energies depend upon several factors which are given below: size of atom, charge of nucleus, screening effect of inner electrons, or the penetration effect of the electrons. Let's now discuss these properties, these factors to appreciate fully the concept of ionization energy. Firstly, we discuss about the size of atom. The ionization energy depends upon the attractive force with which the outermost electrons is held by the nucleus. This in turn depends upon the size of atom because the attractive forces between the outermost electron and the nucleus is inversely proportional to the distance between them. Thus, in a small atom, the electrons are tightly held, whereas in a larger atom, the electrons are less strongly held. Thus, the ionization energy decreases as the size increases. Nuclear charge. With the increase in nuclear charge, the force of attraction between the nucleus and outermost electron increases. Therefore, more energy is required to remove the outermost electron. As a result, the ionization energy increases with increase in nuclear charge. Screening effect. In atoms with more than one electron, each electron repels every other electron and also repelled by every other electron. The attractive force that each electron feels from the nucleus is affected by all other electrons in the atom. In addition, the inner electrons screen or shield the outer electrons from the positive charge of the nucleus. As a result, the effective nuclear charge, that is the charge actually felt by outer electron is less than the actual nuclear charge. Therefore, the ionization energy will decrease. Thus, increase in the number of electrons will decrease the ionization energy. Penetration effect of the electrons. In case of a multi-electron system, the electron in the s orbital penetrate to make the nucleus more than the p orbital. It means that s electron experience more attractive forces of the nucleus than the p electrons of the same shell. As a result, s electrons are more tightly held by the nucleus than the p electrons. Thus, the ionization energy of atoms possessing s electrons will be more than those of p orbitals of the same shell. It is important to note that the elements with low ionization energies are in the lower left corner of the periodic table. Elements with low ionization energy lose electrons relatively easily and form cations. These are known as reactive metals. A careful inspection reveals that elements with high ionization energy are in upper right corner of the periodic table. These all are known metals. Elements with higher ionization energy do not lose electrons easily. The variation of first ionization energy of the element as a function of atomic number as shown in the figure. It is clear from the figure 2.6 that ionization energies are the periodic function of the atomic number. The elements of group 18, the noble gases, have the highest first ionization energies of all group and stand at the peaks of the plot. Helium is the noble gas with smallest atomic radius, has the highest first ionization energy of all the elements. It is the high ionization energy of the noble gases that suggests the extraordinary stable electronic configuration of these gases. Let us now turn to the troughs in the plot where the ionization energies are lowest. These elements are all group number 1. The outermost electron of lithium, sodium, potassium, rubidium, cesium are all s electrons. It is clear from the graph that the single s electrons requires relatively little energy for removal of the outermost electron compared with the needed to remove the other electron. Cesium with the largest atomic radius has the lowest first ionization energy. This is because the s electrons are in new shells farther from the nucleus than electrons in the preceding noble gas helium, neon, argon, krypton and xenon. It is important to note the shape of the plot illustrate clearly from the periodic repetition of electronic structures that occurs on the periodic table. Trends of ionization energies across the periods. It is observed that the first ionization energy increases when we move across a period in the periodic table from left to right. This is because each successive atom has one more proton in the nucleus. Thus, the positive charge on the nucleus increases steadily. But the attraction of the nucleus for the outer electron does not change steadily. For example, in period third, electrons are successively added to the same outer shell. Since electrons in the same shell do not shield each other very well from the attraction of nuclear charge, the effective nuclear charge experienced by the outermost electron in each successive element increases. As a result, the outermost electrons experience a greater attractive forces for the nucleus. This results in the decreased atomic radius as the outermost electrons are strongly pulled towards the nucleus as one moves from sodium to argon, and the ionization energy increases significantly from sodium to argon. Although there is a general increase in the values of first ionization potential across a period, a number of irregularities occur. For example, the first ionization energy of boron is lower than the first ionization energy of beryllium, and the first ionization energy of oxygen is lower than the first ionization energy of nitrogen. It is important to note that the electron that is removed from the boron in the 2p orbital, whereas the electron that is removed from the beryllium is in 2s orbital, because 2p orbital of higher energy than a 2s orbital, and electron is more easily removed from the boron than from beryllium. An oxygen atom has 2 electrons in one of two p orbitals. The pairing of two electrons increases the repulsion between the electron and thus causes oxygen to have a lower first ionization energy than nitrogen. Trends of ionization energies across group. In general, the first ionization energy decreases in a regular way of descending the main groups. Thus, because the elements in the group have the same outer electronic configuration but the different principal quantum numbers. As principal quantum number increases, the average distance of the electron in the shell from the nucleus also increases. Because the outer electrons are further from the nuclear charge of the nucleus, they are less tightly held with the nucleus, and this accounts for the lower value of ionization energy at one moves from the top to the bottom of the group. A departure from the regular trend occurs in group 13, where the expected decrease occurs from boron to aluminium. However, the values of remaining elements gallium, indium and thallium do not continue this trend. This is because gallium atom is preceded by 10 elements of the first transition series. This makes the atomic radius of gallium much smaller than expected otherwise. As a result, the outer electrons are tightly held by the nucleus and causes ionization potential to increase. A similar effect is observed in the introduction of second and third transition series before indium and thallium. This accounts for the increased ionization potential of indium and thallium in the table 2.9 for group 13 elements. Successive ionization energies. All atoms other than hydrogen have more than one electron. The energy needed to remove the second most loosely bounded electron from a mole of gaseous cations is known as ionization energy. Because of the positive charge, the cation A plus attracts electrons more strongly than the neutral atom A does. There is one electron less than the cation compared to that in the form of an element. As a result, electron repulsions are reduced. It means more energy is required to remove the second electron than the first. Therefore, the second ionization energies are always larger than the first ionization energies. Similarly, the energy required to remove the third most loosely bounding electron is known as third ionization energy. The larger the positive charge on the cation, the stronger is the attraction between the cation and electron being removed. In addition, electron-electron repulsions are also small. The larger the positive charge on the cation, the more is the energy required to remove the electron. Thus, for any element, the value of third ionization energy is always greater than the value of second ionization energies. Similarly, the fourth ionization energy is greater than the third ionization energies of an atom. The successive ionization energies from E1 to E8 of first 13 elements are shown in the table 2.10. Ionization energies to the right of the stepwise line involve the removal of electrons from the core of the atom. It is important to note that for each atom there is large increase in the ionization energies after all the outer electrons are removed. Ionization energies provide strong evidence for the existence of electron in the shell in atoms. Let's take an example of sodium and remove all the electrons from the sodium. One can easily see from the table 2.10 that there is a significant increase in the energy needed between the remove the first and second electrons. There is another large increase between the ninth and 10th electron removing. These observations suggest that the increase occurs when the electron being removed has to come from a new shell, the closer to the attractive charge of the nucleus. The difference between the energy levels is so large that the logarithms of successive ionization energies are plotted instead of the successive ionization energy themselves. One can easily interpret the pattern of the figure 2.7 that the outermost shell, that is 3, of the sodium contains 1 electron and the second cell has 8 electrons, leaving 2 electrons in the innermost one shell. It is the large difference between the ionization energies of outer and core electrons that is responsible only one kind of cation, that is group 1 and group 2. Atoms of transition metals have d electrons of the n-1 as well as s electrons of n shell outside the core. The energy of the electron in the n-1 d orbital is no different from the energy of the electrons in the ns orbital. As a result, atoms of transition metals often have more than one kind of cations. For example, iron form Fe2 plus and Fe3 plus cations. Measurement of ionization energies value. Ionization energies are measured to be spectroscopic techniques or in the discharge tube containing the vapors of atom under consideration at low pressure. It is connected to the source of the current. On increase the potential difference, a stage reaches when a sudden flow of current occurs at a certain applied voltage. There is a stage when the gas is ionized or the potential occurs. If we increase the voltage, the further there may be a stage again when there is an abrupt rise of current. This gives the second ionization energy. In this way, we can evaluate the successive ionization value of third, fourth, and fifth ionization energies. In case of hydrogen, the first ionization energy value correspond to the 13.598 electron volt per atom. Thus, the ionization energy of the hydrogen atom is 13.598 electron volt. Thus, the first ionization energy of electron is 1312 kilojoule per mole. Similarly, the first ionization energy of sodium has been evaluated to be 496 kilojoule per mole. Now let's start electron affinity. Atom not only lose electron to form positive ion but also gain electrons to form negative ion. Electron affinity, as a name implies, that it is a measure of the tendency of an atom to gain an electron. If you recall, when an electron is removed from the gaseous atom, energy is required. But when an electron is added to a neutral gaseous atom, energy is released. Thus, we can define electron affinity as the energy given out when an extra electron is taken up by a neutral isolated gaseous atom. Since the energy is evolved during the process, electron affinity has a negative sign. The higher the electron affinity of the element, the more energy is given off when an electron is added to the atom of the element. Thus, the magnitude of electron affinity indicates that how tightly an additional electron is bound to an atom. A high value of electron affinity indicates that the additional electron is strongly bound, while a low value of electron affinity indicates that the new electron is weakly bound. Factors on which the affinity depends. There are several factors on which the value of electron affinity depends, but the most important factors on which it depends are the following: size of atom, nuclear charge, and electronic configuration. A variation of electron affinity down a group. The electron affinity of the elements decreases down a group. This is because both the atomic size and nuclear charge increases down the group. However, the effect of increase in the size is greater than the increase in the nuclear charge. As a result, the incoming electron experiences lesser attraction by the large sized atom and therefore the electron affinity decreases. This is evident from the decrease of electron affinity in going from chlorine to bromine and to iodine. Variation of electron affinity along a period. The electron affinity of the elements increases along a period. This is because across a period the size of atom decreases and nuclear charge increases. Both these factors result in greater attraction of the incoming electron. Therefore, more energy is released when an electron is added. As a result, electron affinity in the increases along a period from left to right of the periodic table. Certain irregularities are observed. For example, Beryllium, magnesium, nitrogen, and noble gases are exceptions. In a periodic table, halogens have the highest electron affinity. Some of the important features of electron affinity are given below. Halogens have the highest electron affinities. Electron affinity of noble gases are 0. Electron affinity of beryllium, magnesium, and nitrogen are nearly 0. Electron affinity of fluorine is less than that of chlorine. This is because the fluorine atom has an unexpectedly low value of electron affinity compared to the immediate next member, that is chlorine. The low value of electron affinity of fluorine is due to the very compact size of fluorine atom. As a result of small size in fluorine, there are strong inner electronic repulsions which discourages the incoming electron to enter the outermost shell of fluorine. Therefore, the electron affinity of fluorine is small. The electron affinity values of oxygen and nitrogen are also small compared to sulfur and phosphorus. Thus, this is also due to small size and high effective nuclear charge. As a result, the very little energy is given off when electron is added to the oxygen. Successive electron affinities. Energy is evolved when one electron is added to the atom. Oxygen or sulfur atom forming the spaces O negative or S2 negative. However, it is difficult to add another electron to the negatively charged because of Coulombic repulsions. In order to force the second electron to add to O negative or S negative ion, a lot of energy has to be supplied counter the Coulombic repulsions and to allow the formation of O2 negative and S2 negative. In other words, the addition of second electron is an endothermic process. The net electron affinities for SO2 minus and S2 minus have a positive value. Although it requires energy to form these divalent ion compounds containing these ions are known, it follows that the energy required to form the ions must come for some another process such as lattice energy when the ions are packed together in a regular way to form a crystalline solid. Determination of electron affinities. The electron affinities value B cannot be determined directly. They are determined indirectly by involving the Born-Haber cycle. Born-Haber cycle relates the lattice energy of an crystal to another thermochemical data. This can be illustrated by taking energy terms included in the building of crystal of sodium chloride. The elements in their standard state are first converted into the gaseous atoms and then to the ions and finally packed into the crystal lattice. The enthalpies of sublimation, dissociation and ionization energies are positively since energy is applied to the system. The electron affinity and lattice energy are negative since energy is evolved in the process. According to Hess law, the overall energy in a process depends upon the energy of the initial and final states. It is clear from the figure 2.9 that the enthalpy of formation of the delta H is the algebraic sum of the terms going around the cycle. All the terms except the lattice energy U and electron affinity can be measured experimentally. By using the non-crystal structure, it is possible to calculate the crystal lattice and hence the value of electron negativity. Thus, for NaCl. Now, since the electron affinities values are known, therefore the Born-Haber cycle can be used to calculate the lattice energy for unknown crystal. Now, let's start electronegativity. Electronegativity is the ability of an atom in a molecule to attract itself an electron pair with the shared atom with another. Greater the ability of an atom to attract the shear pair of electron, larger is the value of electronegativity. For example, in hydrogen chloride molecule, the electronegativity of chlorine is less than that of electronegativity of hydrogen. It simply refers to the ability of the shared pair of electrons between the HCl to lie towards chlorine that of hydrogen. Electronegativity, like electron affinity, increase with decreasing atomic radius and increasing effect of nuclear charge. It is important to distinguish between the electron affinity and electron negativity. Electron affinity is like ionization potential is an atomic property where electronegativity is a molecular property. The Bohr relation is based upon the assumption that the bonds A2, B2 and AB are molecules are purely covalent. However, it was overruled by Pauling that in most of the heteronuclear bonds, of the type AB, the actual bond energy is more than the geometric mean of the energy of AA and energy BB due to some degree of ionic character. Electronegativity cannot be determined directly, but several indirect methods have been used to estimate the relative electronegativity all the given similar result. Because negativities are relative, they have no units. It is not the electron negativity but the difference in the electronegativity of the atoms joined by the covalent bond is important.